In this video, we're going to continue our study of kinetics and look at reaction coordinates and catalysis. And this is going to help us see a bit more about what's going on as we look at a chemical reaction that goes from reactants to products. We're going to see that there's a bit more going on than just sort of the state function beginning and end look that we've had previously. And we're going to learn about the energetic changes that occur as something goes from reactants to products, which we'll plot on what we call a reaction coordinate. We'll also look at how catalysts can help change a reaction, and this will contribute to changes in the kinetics and a general speeding up of that reaction. As we think about the role of a catalyst and activation energy, it's really important to know and understand what a reaction coordinate represents. So here we have a reaction coordinate, and we're looking at a reaction that goes from two reactants, A and B, to two products, C and D. And we can track the progress of this reaction over the course of this reaction. So basically, as it goes from 100% reactants to 100% products, we see from the left to the right. And note that as we go from reactants to products, there's an unstable or high energy transition state that's in the middle. Basically, there's some rearrangement that needs to occur that is the most unstable thing. There's some barrier to getting from A and B to C and D. And that kind of makes sense, right? Some bonds need to break, some bonds need to form, and this transition state represents bonds being broken and being formed. So this particular reaction we can see from the reaction coordinate is actually exothermic. We can see the energy on each side, and we see that the final energy is lower than the initial energy. In every case, whether it's exothermic or endothermic, spontaneous, whatever, we still have a more high energy transition state that we must overcome. Even though this releases energy, the transition state is still the highest energy point between those two. We can measure the enthalpy change for this reaction, if this was measuring enthalpy, by the difference between the reactants and the products. And we can measure EA, the activation energy, as the amount of energy it takes to go from reactants to the transition state. And these are both very important characteristics to know from a reaction coordinate. Okay, so here's a question for us, right? And go ahead and pause the video here and try to answer the question. We're asking, when a reaction has a larger activation energy, what do we know about its transition state compared to one with a lower activation energy? All right, hopefully you've gotten to get a guess at this one, or an educated guess, right? And the answer is the transition state is less stable, right? When we have a larger activation energy, that means that it takes more energy to get through the transition state, which means that the transition state is likely less stable, takes more energy to get to it, right? Remember that unstable compounds are generally associated with high energy complexes, and the more stable a transition state would be, the easier it's going to be to attain that amount of energy required for the transition state. For our next question, let's look at which of the following generally describes an exothermic reaction. Go ahead and pause again and see if you can come up with an answer. All right, hopefully you've chosen a selection for this one. The answer is D, energy is released, right? We've learned about endothermic and exothermic reactions already. Endothermic, heat required; exothermic, heat released. This does not say anything about the rate of the reaction. We can have exothermic reactions that are either very fast or very slow. This is not determined primarily by the exo or endothermicity of that reaction. Cool. Again, it's defined as releasing heat. Rate is not necessarily affected. When we're looking at these reaction coordinates, it's very useful to consider the reverse reaction because this can show very important characteristics of that reaction as well. So in reverse, we just kind of flip everything around, and here's that graph just literally reflected. It looks a little bit weird, but now we can see pretty clearly how C and D goes to A and B. And note here that we have a new activation energy, because if C and D are the reactants, the energy defined as the activation energy is to get from reactants to the transition state. This is now a bit greater, as this was an exothermic reaction as previously written. Endothermic is written now, and the activation energy is between the reactants and the transition state. Note that delta H has switched sign, which is indicative of what happens when we reverse the reaction as well. If it released X amount of energy going from A and B to C and D, it will now require that amount of energy moving forward. The reverse reaction has flipped its behavior and is now endothermic. Okay, Let's try another one. Which of the following occurs at a faster rate? So basically, how does activation energy affect rate? And we haven't talked about this specifically, but hopefully you can kind of figure it out, make a good educated guess, or use what you've looked at from the reading and see what you come up with. All right, hopefully you've had a chance to log a response for this one. Key to understanding this is to remember that temperature is a distribution, and while most molecules have an amount of kinetic energy around the average, which is described by the temperature, it's a distribution, right? And so even at a given temperature, there will be some with more energy than average, and a rather small proportion, but an existing proportion with a lot more energy than the average. And remember that it's one of these that needs to overcome the barrier. So when we think about this, what we want to think about is with a certain barrier, which one is going to allow more molecules to jump over that barrier? And the answer is with a small activation energy, right? There is no negative activation energy, it's always positive, but if that barrier is smaller, then more molecules at a given temperature will have enough energy to overcome that barrier, and therefore the reaction will proceed quicker as more molecules are able to have that amount of activation energy. One more, go ahead and pause again. Catalysts, how do they increase the rate of the reaction? And we'll study this in just a second, but for now, see if you can log a response. All right, catalysts, how do they increase the rate of a reaction? Haven't talked about this, we will soon, but perhaps you've seen it from the reading. They do so by stabilizing that transition state. So remember, catalysts generally speed a reaction, but the way they do this, chemically speaking, is they create a more stable transition state, lower the activation energy, and as we looked at previously, that increases the rate of a chemical reaction. The way catalysts often achieve lowering the activation energy is by creating a pair of transition states, and we can see this contrast between the red uncatalyzed reaction and the blue catalyzed reaction shown here. Catalysts will often break the one reaction into a pair of reactions, which means that there's two separate transition states. However, there's still only one activation energy, as that is the amount of energy to get from the reactants to the highest energy point in the reaction coordinate. And making that highest energy point lower means that the reaction can be sped up as more molecules will have enough energy to overcome this barrier. Very importantly, catalysts do not change the reactants, the products, or the overall energy change of the reaction. They keep everything pretty much the same, and because, as by design, they are consumed and then regenerated in the reaction, they are able to just have a tiny bit facilitate the entire reaction. An example of this is an enzyme, which is able to hold reactants in place, and then once the reaction is complete, they leave the enzyme and the enzyme is able to complete another reaction turnover. The last thing I want to talk about is the Arrhenius equation, because while we've talked about temperature, the rate constant, and the activation energy, this is an equation that brings all these relationships together. And the first thing we want to do is remind ourselves about the definition of temperature, which we've alluded to a bit, but remember that temperature is a distribution of the kinetic energy, right? It's the average kinetic energy, and if we look at graph A in red, we can see that this is basically a histogram showing the distribution of the kinetic energy of the molecules. It's a bell-shaped curve. Average is what describes the temperature, but still some molecules have much more energy than the average. If we increase the temperature into B and we show T1 versus T2, where T2 in black is a high energy sample, here we see that the whole tail has been shifted and there are more molecules, greater area under the curve, with more kinetic energy than is needed to overcome the activation energy, EA. Now, this is similar looking to a reaction coordinate, but this is not, right? This is a graph that's very important to know, the distribution of kinetic energy within a given temperature of a sample. Now, Arrhenius is going to relate these things that we've looked at already, the temperature, the rate constant, and the activation energy, as they're all related through kinetics, right? Basically, the highest energy particles are able to react, so if we increase the temperature, that can increase the rate, more high energy particles. Simultaneously, if we decrease the activation energy, there will also be more high energy particles. And this equation will sort of drive home how they're all related. Now, here's a version of the Arrhenius equation. K is our rate constant, EA over RT. So we have K, we have the activation energy, and we have the temperature here. But perhaps more useful is if we take this and we make it into a slope-intercept form equation by taking the natural log of both sides. Because this allows us to have this constant A fall out, which is a factor relating to the collisions of a reaction, which we may not know or be that interested in. And this final form is probably the most useful for textbook equations because it relates the rate constant at multiple different temperatures. Simultaneously, it also shows that if we know the rate constant at multiple temperatures, we can get the activation energy. This can also be used with a large set of data in order to fit data to this linear equation and get the activation energy or something like that, all of which are really good activities to work on out of textbook equations in the homework, and they're all dependent on the Arrhenius equation, which shows this relationship between these parameters we've studied in this video. Note that in the Arrhenius equation we could use rate constants, but we could also have a pair of rates that'll still give us a ratio that's in line with something we can calculate in Arrhenius. Mentioned the linearization before. Here's just a brief breakdown of how we would do this, right? Again, here's our Arrhenius equation. With the natural log of both sides, we get the following. And note that this is a linear equation if we're to say that y is natural log of k and x is 1 over t. This ends up mapping out the slope to negative EA over r. And basically what this means is if we take the natural log of k, so say we have several rate constant points and we have corresponding temperatures, we plot the natural log of k versus 1 over t, we should get a linear fit with a slope that's equal to negative EA over r, and then we're able to calculate the activation energy from this plot, from the data set that we have obtained. As one final note, remember that a large activation energy has a high sensitivity of the rate to changes in temperature, so if you are running these experiments, that's something you can expect to find.